So we just want to start, and as I already promised today, switch to high. It's not so much basically a new is how to calculate. As we start beginning, so 6 to 6.1 is just an introduction and basic definitions. Yeah? Let's say introduction. It's clear. We need two signals to represent symbols to be transmitted. In the Bodel transmission, we just represented bits, but here we may say of the symbols 0, 2, 3. Or so now. So this is the number of symbols, different. Signals. Si of t to represent discrete symbol states examples. Say the symbol states are 0. Here the modulus would be 4. Let's say in a different example, depends on the modulation scheme. 3. 3. It's also for the order of 4, but with a by thing. So we signs, as you can see. This means if we have capital M discrete symbol states, transmit 2 of M. It's usually M two. These books schemes are investigated. This M is usually. It's usually. And of course, if we transmit log2 of bits, yeah, say 4 bit rate. It's denoted TB. This is the reciprocal value of TB. Interval. In other words, the simple interval. This is just that's clear. And so-called symbol rate, the distribution. Symbol. What is the rate? This rate is discrete symbols to be transmitted, say with the levels generate. This is the question. And the symbol rate is, depending on the bit rate, symbol for this. It's just the reciprocal variation interval. This is, of course, yeah, it's bit rate for binary modulation. represent, or with which symbol we represent log 2 of m. This is measured. You can say symbols per seconds, or if you have since we reduce the symbol, depending on the scheme, we may require less bandwidth. Depends on the modulation scheme. If you use, for instance, orthogonal signals, this is not the case. But for ME2, yeah, for instance, for amplitude, this would be the case required. Bandwidth. This is usually why we use high order modulation. We use bandwidth for a given transmission bandwidth can achieve, depending on the by-or-not ratio at the receiver, really a higher data rate. Then we have to say, until now we talked about the mean. Say, what is the mean G per symbol? Symbol transmitted. This is, of course, we use instead of a or bit here as an index for this energy. This is just the average value where we always assume all the symbol states have the same probability. This is just the mean. So I EI, these energies, of course, are the N signals, where I assume mean signals here. And take a look here, duration limits. If we would assume signals are restricted, symbol interval capital T, 0 to capital. But since the last lecture, we know it's possible to use pulses duration which is longer than the initial interval. Sampled value of the interpolation function for this one-dimensional, this needs to be single direct delta. If we sample, it's a step size of capital T. But necessarily to restrict the duration of the pulses, transmit sequences of pulses, of these signals interval Nyquist criteria. Then, since we have log 2 of m, so for instance for a module, we have within each symbol, energy per bit interval is just the energy symbol divided by log. Easily see it because is log 2 of m. So these are simple relationships. And then just as it's not complete, but let's say most important approaches for such modulation schemes, most approaches, this is an abbreviation. Let's say, by the way, the names are not unique. Some books you read this name and some book you read this name. Traditionally, if we talk about baseband transmission, let's say here on the left side, baseband transmission. Baseband, this means the spectrum centroid is at low frequency is transmission. Let's say you want to transmit about a copper cable. Example to transmit at radio frequencies, let's say. Then a very important relation scheme is just pulse amplitude. So pulse amplitude it's clear, yeah. Then we distinguish usually bipolar modulator. I don't want to show you details. See it in the next section. Study it on your own. Simple. But if we take a look at signal space, yeah, just draw an example for M to 4 here on the side and then side. Let's say, so we have pulse amplitude modulation is just one dimension. So this C1 of T, our basis function, could be rectangular. So be such a raised cosine pulse. Let's say 0. Say coordinates. I only show the coordinates of signal vectors. One signal vector is here, the other signal vector is here. This would be antipodal modular. But I want to show m equal to 4. So we signal vector. It's a distance d min. Let's say we have to 4. This is an example of spaced distance between the signal vectors. This would be, say, our minimum distance. It's not the Helmholtz distance, it's the Euclidean distance. As yeah, switch to say unipolar approach. Is the 0? A unipolar weighting of this function. Space, by the way, and say the same spacing. Yeah. Still this one polar. If you calculate the scheme, energy per symbol of the right-hand side scheme for the same d min, by more energy. So both examples are to 4. But as I said, the names are not switch to bandpass transmission. So let's say we want to transmit over a radio frequency transmission. Say optical transmission would be also an example. I just use this abbreviation RF. See transmission. Could do, of course, you learn this examine scheme, shift key. Oftenly, I write it, yeah. Change the phase of a sinusoidal key. Radio frequency transmission, sinusoidal carrier somehow, and often, but not always. Yeah. This term keying, if you talk about bandpass transmission and just pulse. This is not you. This there's a very Messerschmitt suggests some chapters, and they just use pulse amplitude so in the band. By different names, but I just tell you. So in phase shift keying, let's say we make just an example. Basis functions, of course, yeah, are let's say a rectangular wind sine and a sine wave. So our quadrature pair. So we have basis functions. Yeah, they just differ in the 90. Then all the signals have the same. This means they also have the same symbol. You can write here this coordinate just square root of symbol. Then let's say for m equal to 8, coordinates. This would be level phase shift key. Yeah. And this would be the signal space of phase. All the basis functions, yeah, are to be a pair. It's a 90-degree social care. So our pairs which we use for quadrature up conversion. Then, of course, amplitude shift key. But amplitude shift key is exactly the same as pulse amplitude. So there is no difference in the signal space. Is if we use the term pulse amplitude, we may to speak about say baseband signals, signal wave, like just rectangular transmission, to use upconverted. So you could say these are just, I hope this works, these two signal spaces, but for a basis function which is appropriate for radio frequency transmission. So we just need to do, let's say, an upconversion of these signals with a cosine or a sine wave. So it's exact. You could say there is no difference between PAM and amplitude shift keying. Usually this shift keying is used for bandpass signals. So you can, again, distinguish between bipolar and unipolar. Then there is this most important scheme, I would say. This is quadrature amplitude modulation. Don't use this shift keying. And in short, you could say this is basically a quadrature upconversion of two bipolar PAM data streams. So this is PAM. So we say just as a short version, this is quadrature or quadrature upconversion, sine and minus sine upconversion. Two bipolar, always bipolar. So, and then signal space could look like this, but later we also discuss an example. Signal space, again, dimensional. This is functions C1 of C2. Let's say we talk about a 16-level PAM. Our levels for bipolar amplitude. So we change the amplitude, let's say, of a sine with 4 levels, but also of a sine with 4 levels. Total combinations. Principle is just a parallel transmission to bipolar PAM data streams by means of a detect basically a signal component in this direction and in this direction. So this would be the signal space of PAM, of quadrature amplitude. And then less important, this is frequency shift key. So we change the frequency, signal to code the information. And this is usually orthogonal signals. But in my opinion, signals today, only binary phase shift keying is a meaning. Because if you use more than 2 frequencies, you need more bandwidth to obtain an energy efficient transmission. But if you do coding, as you have learned in the last lecture, channel coding, you are much more efficient at the situation where you use orthogonal signals. So if you use just very, very simple codes, which are orthogonal, as good if you Solomon code, C codes, whatever. It's not near. So, but just to show you a signal space, let's say now we have also 2 basis functions, but now achieve orthogonality just by changing the frequency. It's a cosine with some frequency and another cosine with a different frequency. bandwidth. Let's say one signal is here, yeah, signal vector is here for binary phase shift keying. This would be orthogonal transmission. So, and now, next thing, and again, there's not so much to learn. This is 6.2, optimum minimum distance detection. Distance detection. Basically, we know everything. Just have to switch from the with one basis functions to capital N basis functions. Assume one-shot transmission. This is what we assume. Transmission. What does it mean? Only consider the transmission of Si of t. Yeah, this is what it is. So only Si t transmitted. So we analyze the transmission of Si of t and not Si of t minus k times capital T. So we also transmit signals, of course, for the adjacent symbols to be transmitted for 0. So there is only one single symbol transmitted. And the cost function, yeah, or the decision is based on the mid distance. We know this decision. It's based on what? So we say S hat, let's write here still of t. Our estimated signal is arc min, as we know. There's no difference, yeah? Over all possible signals Si of t. And we want to minimize this cost function. And our cost function is just basically the mean g of the difference between the received signal and all possible transmit signals with cost function. This is easy to understand, as you remember. So how do we measure a distance? So we say, take the difference of the received signal, all possible transmit signals. So I go. So we measure the difference. This would be the energy. Oh, no, this is not the energy. This is just the square, yeah? But if we want to measure the energy, we could do this like this. Again, take care. And also write, yeah, from 0, let's say, to capital T, if you say we restrict our signal duration of symbol and type. If we use, for instance, root-based cosine pulses or whatever, signals are longer than this capital T, therefore I wrote here with this notation. Maybe on the slides it's from 0 to capital T. But then it's also mentioned we restrict our attention again to signals which are not longer than the symbol and type. This is the cost function, but we can say, simplify this. Yeah? Don't need to calculate, let's say, capital M cost functions in this way. I forgot T here. Yeah, we can simplify it with simply express our signals by means, yeah, of the orthogonal components. So we say with Si of t is just sum goes from 1 to capital N, this is the dimension of the signal space. So we can decompose our signals into capital N orthogonal components. And we write here Sij times Cj. So N is the dimension of the signal space. And with this approach, we find also we can simplify this J. This J, our cost function, is, let's say I write this in because we don't need this. This is the energy of received signal, T, is this expression, yeah, which is basically J go up. Let's write it like this. J goes from 1 to by J. This is basically the energy of the received signal in our signal space. But both expressions, both terms, do not depend on SI, so we don't need them. Not required. Or in order to make our minimum distance decision. Why? Because they don't depend on SI of t, as you can see. You can write this, independent on SI. And now there's the important part. Thus, sum J goes from 1 to capital A. Then we just get here by J SI square. See, this is what we need for this J, because this depends on signals themselves. And we can say this expression is nothing else than sum up always the difference of the vector components. We up with this y SI as vectors. This would be just squared lengths of the different vector. So this leads to our simplified distance detection. So what we need to do is we can estimate transmitted signal just by argmin for this minimum distance detection over all possible transmit vectors, and we just minimize the distance, again the Euclidean distance and not the Hamming distance, between the received vector all possible transmit vectors. This is our decision criterion. Quite simple. And as you can see, what we need to do is we need to obtain y. So the components of the received vector in our signal space. Maybe we write here where. Don't need to know this to build the optimum detector, but we know this received vector is just a transmitted vector plus a noise vector. And now this becomes useful. Yeah, this is the noise vector, because if you wouldn't have noise, the received vector would be identical to the transmit vector, so there is no distance. Yeah, and with respect to the noise, it's interesting because only the noise which is projected in our signal space can affect our signal. Therefore, this is the noise vector, and it's only the noise components in our signal space. Yeah. Now, if you want to have an example, let's say, how does the detector look? Example for, let's say, n equal to 2. The general case is on the slides. Yeah, and then, but I want to show you, you don't need to use a correlate. You can also use these matched filters. So based on, and in this example, since in my assumption, I don't know the position of the signals, because they could cosine or whatever. Based on non-causal unit energy filters. So how does the detector look like? Then you only, signal space is two-dimensional. Yeah? Instead of using two correlators, yeah, here two matched filter, one for each orthogonal component. So the main pulse response for the first matched filter is just this, C1. This is non-causal. So, but if I don't know the exact duration of C1 of t, it's easier for me just to write this, to say, okay, sampling time is just at 0, of course, in this case. It's a second matched filter which is matched to the orthogonal component signals. Of course, if you build this receiver, yeah, don't need to use, but the signal to noise ratio at the sampling time is exactly the same. So in the t equal to 0, then what comes out here basically, this is here, this is, let's say we denote this as y1, this is y2, because our signal space is two-dimensional. This two vectors. So what we see here is basically our received vector, and then we do the decision. This decision is just to this procedure here. So that's why we know about transmit signals decision. And what is really important, and this was also shown by a seminar task, if we now look at expected value, this has some importance. Let's say we take a look of this noise of the Jth component. If we take a look at, say, K, so this is the noise, yeah? And the components, N. So two components are, no, this is difficult to say, yeah? Expected value, here we have to consider a random. Random variables are usually, therefore here it's capital. Then, these components are orthogonal, expected value 0, if we take a look at different output, so for J to K. This also means, since the noise is Gaussian distributed, that this noise here at this output is statistically independent. And then, if we use this unit energy filters, yeah, this variance, yeah, the pulse response is unit energy to K. So we just take a look at the power at one output. This is exactly the same as the noise power spectral density. This is strange, but this is just, the reason is just because we use. That's basically everything. Okay, I have heard about maximum likelihood. For instance, in information theory coding, and let's short discuss this, let's say, proof of optimality. So, start with this. Detectors usually use so-called maximum likelihood criterion. It's maximum likely. Does it look like? Then you say S hat, so the estimated signal, yeah, is just arc max, and it's easy to understand. It's not arc over all possible transmit vectors. And take a look at the probability density function. This is an abbreviation. Yeah, I just don't use this indices, but I think you understand why it's written here. Just to save time, if we take a look at the additional probability density function for a certain transmit vector Si, choose this transmit vector, which leads to the highest probability received vector. So this is a conditional. If Si is being transmitted. Of course, we can use this expression for this maximum likelihood principle using the vectors, because the vectors contain all the information in signal space. So the noise is already restricted to the noise components in our signal space. And now we choose this transmit vector pitch for a given received vector y, just the highest probability. So which leads to the likely received vector for this transmit vector, basically. Now we want to check, is this maximum likelihood criterion is this y, yeah? Choose this as I to the highest conditional probability of this y as I. Is this identical to the distance criterion? This is the question. And the answer is yes. Is like criterion identical to distance criterion? Until now, we talked about minimum distance, right? Just want to show you this is quite simple. If you take a look at one component, so say J, yeah, this is the Jth component. Say conditional of J given a certain transmit Sij. So let's say we have at least two possible transmit signals and we take a Jth component. Then of course, since we have Gaussian noise, this is quite simple. Noise variance is n naught by 2. So this means 2 pi and this expression. Then Gaussian noise, value of this noise is 0. This means if we transmit Si, J, yeah, it's just Yj Si square with a minus sign divided by 2 times n naught by 2 divided by n. Now the question is Yj minus Sij. This is just, of course, this component is this vector component. Transmit Sij. So would exactly receive Sij if there is no noise. But there is noise, then we receive Yj. So what we see here, this difference is just Gaussian noise. And the center of this Gaussian noise is at Sij. Let's have an example. So let's say we discuss a simple example where we only have, so where the signal space is only one-dimensional, then we have this one component, m equal to 2, let's say. This example is so-called on. It's quite simple, similar to this antipole transmission, yeah, but it's similar to antipole transmission, but one signal vector is just, oh, this is what I want. Signal vector is just 0. Signal vector is, of course, so we switch the signal on and so let's say what happens if we transmit a 0. These are the amplitudes. Y1, J is 1, of course, there is only one component. So, and then I assume that we transmit, say, S, it's just 0. It's 1. It's 2, 1 is just square root of 2 eV. So the mean energy per bit, because M is 2. Yeah? Energy per bit, the energy of this is 0, the mean is 2 eV, so the mean energy is eV, or equal probability signals. So if we transmit a 0, what we receive is, of course, negative Gaussian noise plus this 0. It's like this. Yeah? So this is what we draw. this is the conditional propensity function. I don't use the indices to save time of y1, given that S11 has been transmitted. Now we take a look at what happens if S21 has been transmitted. Then let's say the average value without noise is this value. But with noise, yeah, I get this. Also, I still have the same noise variance. See this in this figure. Yeah. This would be F, given that S21 has been transmitted. Now you see immediately, but we generalize this for the multidimensional case. If we now have a received vector component, let's say this is what we receive. This is the concrete value. Let's say this is what we concretely receive. I denote this as received, yeah. And then you see the probability distance now to this vector, yeah, is much smaller than to 0. But you see the probability of this is much higher than the probability of this. So there are two probabilities, yeah. This probability and this probability. And the probabilities are exactly equal if the distance from 0 to this value is the same. So you see the minimum distance criteria is exactly the same, yeah, as this maximum likelihood transmission. Of course, in this case, for this concrete received vector, it's more likely that S21 has been transmitted. This is more likely than this has been transmitted. So we choose S21. We choose it because it has a higher probability, but we can also argue choose it because the distance is lower. So I just tell you this is exactly the same. Now, say in dimensional case, it's quite simple. So for what do we get? Then we get F, so conditional probability function of this concrete of the received vector, transmit vector, and then since the noise is statistically independent, correlator output or match. I mentioned this before, because there are orthogonal these components. Yeah? Noise, they are statistically independent. Since all the outputs are statistically independent, multiply the individual density functions. So product of the probability density functions as given here is just, okay, say, to use the answer itself. And here we have product from 2 capital. It's the same expression, e to the power of yg si squared. If you take a look at the product, you can simplify. If you have a product of exponentials as if you do this, you get simply this expression. Oh, this was my microphone. Get simply this expression. This is the same as e to the power of minus I squared. Because if you calculate the square of the distance, yeah, you get just the sum of yj minus sij to the square. Take the square root, it's just Euclidean. It's exactly the same. Then you see, yeah, you maximize the probability if you minimize this distance. See this. The smaller this exponent is, the higher the probability. So this means, yeah, maximize f b distance. square of. So now you can see, okay, maximum likelihood is exactly the same as our. This was the proof. Just a note, but I don't want to discuss here. If you take a look at the so-called MAP criterion, MAP criterion is basically very short, maximum a posteriori. Then we say estimated signal is. It's a slight difference. We change the order of the probability of Si given a received vector y. So it's just a priori we want to choose the transmit vector, yeah, which is the most likely one for the received vector. And then there is only a difference, yeah, if our transmit vectors would have different probabilities. So let's say in binary transmission, in 99% of all cases, you transmit a 1. 1% you transmit a 0. And then you could say, let's say, if the distance between this case, if the distance between, let's say we are here, yeah, distance between the 0 and this received coordinate is slightly larger than the distance between the received coordinate 1. But in most cases, you transmit zeros. Let's say in almost all cases, you know it, you transmit zeros. You could say, oh, I still decide for a 0, although the distance to the 0 is larger than to the 1. But this only happens if we have signals with different probabilities. In this case, yeah, you would have a criterion which looks like this. S hat is equal to argmax. Just write this. Which looks like this. We can still use our conditional probability density function before, but then we have to weight this with the probability of this current transmit vector. But this is the same as our criterion. So this is still the, if you wouldn't this, yeah, this is just our maximum likelihood criterion. So this means probability of all SIs is just 1 by capital F. Same probability. Yeah? Again, this expression does not depend on SI. Then MAP criterion is the same as the maximum likelihood. But usually, I've never seen a receiver which uses the MAP criterion, because I don't know examples where the probability, the symbol states, is different. So you transmit, for instance, in binary case, a lot of zeros and a small number of ones. That's all. So this means MAP is the same as maximum. Equal distributed, but which we always assumed. And otherwise, our calculations, for instance, for energy per bit, mean energy per symbols, would be wrong because we assumed equal symbol states. So, yeah, but only very short because. Talk about this after the lecture. Is this possible? Is it required for all the others? We discuss it later, okay? Then you just came here, and if it's really important, I can write. Sorry for this. And now we talk about symbol error rate. Now we know how it works, but we want to know how good is it to estimate it. Or if you have want to ensure certain, what is the required energy per 6 symbol error rate? Symbol. this abbreviation. And we start with a intuitive situation. We discuss for the first the bit error rate of a general line. Binary modulation scheme. In this case, the signal vector looks like this. I do it with 2 dimensions only, but you see and understand that you can use any dimension, say 3, 4, 5, whatever, and still everything is valid. Because this is how laws physics, So we have, let's say, 2 basis functions. Let's say we have one signal vector which is in signal vector. It's this direction. Signal vector points. These are the 2 signal vectors. This is S1. This is S2. Now we can think what happens if we do a minimum distance or maximum likelihood detection. So we could say, basically, I just showed a little bit. This is the called received vector without noise, and this is the called other received vector without noise. Say, if somewhere in this area is a received vector, how do we assign a transmit vector? Then we could say, if we use this minimum distance criteria, have basically could say this is the distance, the length of this line is exactly the minimum distance between the signals, of course. Then if I say I go just in the middle of this connection, just let's say, then I say I use a rectangular window. This would be just decision threshold to decide all the received vectors on this side are assigned to S1 because the distance to S1, this side, is lower than the distance to S2 if I side of so-called decision areas. All the received vectors on this upper area are assigned to S2 according to this minimum distance, and all are assigned to S1. So we denote these areas as decision area. According to the maximum likelihood or minimum. Now let's say, immediately see that this vector here, if n vector, let's say this is a vector, I denote the vector, let's say, as delta. This vector is just, let's say, S2, S1, and this vector immediately see length of this delta is just our d. Then I could say, okay, I just take a look at the component of the noise which is projected on this vector, and if this component exceeds basically d min by 2, then I would make a decision. So let's say I transmit S1, the vector component, the projection of the noise on this vector is larger than d min by 2 in this direction, then I could say now I introduce noise in this figure. Let's say the noise is, this is the noise vector, okay. Say I know, for this figure, this one has been transmitted. This is the noise vector. So what I receive, so this is n, what I receive is, I don't draw it, is of course S1 plus n. This is what I receive. This is the received vector. Now I decide, okay, if I take a look at these decision areas, I know I decide to S1. It's correct. But you could say, now I take a look at the projection, this noise, just on our vector delta. This is the projection. And I say the length of this projection, of this projection, this is n delta. This projection, in this direction, of course, of 2S2, is longer than d min by 2, then there is an error. So this means only the projection of the noise on this vector which connects S1 and S2 and which has the length d min is important. Yeah? Then we could say we just calculate n delta, and if you want to calculate n delta, you can do it on your own at home. If you have to calculate the inner product between delta, so we know delta is the connection between S2 and n and the noise vector, divided by the length of delta, which is d minor. So this is what we have, and now you can insert the value. And now it's interesting. If we now take a look at the variance of this n delta, because we need statistical description of the noise. And our noise vector, of course, noise vector has here two components. N is the components, basically N1. This is our noise vector. But we are only interested in the projection of the noise on this vector delta. And therefore, I'm taking a look at the expected, so at the noise power in this direction. So how is the noise projected on this vector delta? And if I calculate this projection, you just have to insert here the inner product. Write this, because you try it. If we now second moment is n delta, again, there's this problem. It's capital letters here on random variable. And then this is again an. And this is a quite interesting result. So we have in this direction exactly the same noise variance, and not by 2, as these components expected by square. We use this unit energy correlators or filter. Then it's clear if we now, I mean, this is not astonishing, because you could say, if you come from physics, I have a physical law and I use a certain coordinate system. If I rotate the coordinate system or shift the coordinate system, all the laws should be still the same. If I rotate the coordinate system in order to switch, let's say, and shift from a two-dimensional scheme to a one-dimensional scheme, just introduce a new coordinate system where both vectors lie on one x. Then I only need. This can be done by a coordinate transform. Then it's clear the noise variance should be still and not by 2, because physical laws are not allowed to depend on rotation or a shift in the coordinate system. So this is not astonishing. Now we know, that's quite interesting. We can now say, now we statistic of this noise projection, and say, now I know, or here again, such a Gaussian distributed component. This is basically F, say NG. This is the amplitude. This amplitude is Gaussian distributed. And then I say, for binary transmission, if the noise in one direction, it doesn't matter in which direction, is larger than d by 2, half of the Euclidean distance, the length of delta is d min. half of the, then it's clear, then I get an error. So we can, absolutely important result, we can say for any binary transmission scheme, find the bit error rate. This bit error rate is always this complementary error function in all integration, yeah, or excursion distribution. Then this probability is always by 2 divided by square root of, for this square root of, not is just because noise variance is a not by. So this is the result, and this is we now have, say, independent how this binary scheme looks like. Only depends on this DB. This is for on say we make an example as so of k C1. So it's the min just same as square root of function of is equal to square root of 2EB divided by 2 means then square root of, this is the bit array. This is how simple it is. For antipodal transmission, the distance is, let's say, square root of C. Now the distance is 2 times square root of EB, right? In this case, the bit 1/2. It's 2 times better. So this means a certain noise power spectral density, which is, this is your channel. Here, twice as much energy per bit, in the same bit error. As a penalty compared to antipodal transmission of 3 dB. Now, important. Now we switch to the so-called nearest neighbor approximation in order to find symbol error rate any transmission scheme which uses more than 2 signal vectors. Or we use the so-called approximation. I just present an example. And the equation is of course on the slides. If you understand this example, you understand everything. So now we switch to 6. This is the nearest neighbor approximation. Approximation. So as I said, I make an example. Say we talk about level quadrature amplitude. Since I discussed quadrature amplitude modulation, I present a little bit more than required to produce this nearest neighbor approximation, okay? So what we need here is only the signal space, yeah? But I also show basically possible basis functions, yeah, to show you how do the basis functions of quadrature amplitude modulation in the bandpass range look, example. But we would only, for this approximation, we only need signal space, nothing. Let's say this is our space. I start with the signal space. So this is psi1 of, but then I give you psi1 of t. This is, let's say, psi2 of. Now, it's quite simple. So we use a parallel transmission of 2 streams. Let's say one stream has 4 levels. The other stream has 2 levels. So this gives 8 combinations. Or let's say we transmit 2, 3, 4 levels in this direction. So don't do it. Yeah, if it's one-dimensional, then we signal space as we have shown. It's X. So, but now I say I use these 4 amplitudes on this basis function. So I modulate the amplitude of psi1 of t with 4 levels. This means I could assign, I do it here, let's say the bits zeros. Just to see that with 4 levels, I transmit 2 bits. So let's say this would be the bit 0, 1, it's 1, 1, 0. Then I transmit independently a different bit with 2 levels with respect to other basis function, yeah, which is orthogonal. Then I use only 2 levels. This would be 8 bit 1. Then I could say here is a different bit. Let's say again I start here, I assign here is 0 and here a 1 in this direction. Then I have at the end 8 combinations. Of course, I only show the endpoints of the signal vector. These are the endpoints of the signal vector. This is the signal space of, see, I arrange the signal vectors in order to achieve that neighbors, yeah, neighbors all have the same Euclidean distance, of course. So we see in this diagram, this here, this is just the minimum distance. But you can see it, of course, also in this direction. This is also distance. If you have this, then it's clear that this coordinate could be also written as, if you want, here this coordinate is the min 2. So in the other direction. If you want, we can also draw now very short decision area. Because if I only want to decide is, for instance, this or this amplitude, then here decision basically. But then I also need to decide, was it this signal or this signal? Then the threshold would see, it's quite simple to find here, this decision area. So we have one threshold, yeah, to decide this bit. It's only a single bit. And then we have here 3 thresholds to decide the amplitude with respect to psi1. Then we have this decision area. This is one. This is another. This is another. This is an area. This is an area. This is an area. See it? These are the decision areas. Again, I just show you the decision areas. This has nothing to do with the neighbor approximation. So now, I said, yeah, in order to understand what happens in quadrature amplitude basis functions, if I assume, just for my figure, not in reality, say, usually, not always, there are examples where this is the case. I say, okay, I want to frequency of this quadrature pair, cosine and sine, which is not as large as I want to draw. This figure, I could assume that, say, psi1 of t looks like, say, this is 1 period sine. This is the symbol, and of course, for this figure, I assume rectangular shaping, not cosine pulses. This is cosine, yeah. So, and then if I have in the baseband rectangular pulses, yeah, with a cosine. This would be one basis function, it's a cosine. But you could say in practice, I realize this by introducing rectangular pulses in the time domain. This is capital T, this needs to be 1. Sorry. Square root to ensure unit L. Other basis function is per definition minus sign. This matches our quadrature or dependent slope-path transform. So if I draw the other basis function, it's just a minus. But this is a definition. Of course, a sign is also orthogonal, but we define minus sign. So I start here. It's a zero crossing, and here's this would be in this example. But this is just to now let's calculate the symbol error rate. So what is the probability of that one symbol, let's say I transmitted this, yeah, is wrongly detected? See, if I transmit a certain symbol, let's say this one, if I would receive this one, I would introduce several bit errors, symbol error. Basically, now if you want, we assign the bits for this modulation scheme. So we could say these bits could be 0, 0. This could be and I attach that one. That's how I could design the bits. 3 bits in order to represent 8 signals. Signals represent, but now the symbol error. Say, in most cases, in almost all cases, if the noise is not too large, if the noise is not so large that even channel coding, and it's very likely that if there is an error, then the neighboring symbol is wrongly, because the noise leads to an error in the neighboring symbol. This could be explained probability that the noise leads to a wrong detection in the neighbor position is much higher than detection, for instance, of this symbol, because the distance here is much larger. And even the detection, if I transmitted this, the probability that I receive this symbol or this symbol is even higher than this symbol, because the distance of this symbol to this, square root of 2 is larger. And it's much more likely that I wrongly detect this neighbor. Nearest neighbor have this distance d min. So and therefore we can say the symbol error. So I just count the number of nearest neighbors. The probability that one signal is wrongly detected as one nearest neighbor, this is known, and this is 1/2 the error of by 2 divided by square root of. So since that this is wrongly detected as this is exactly this probability. Now what I'm doing is I just count the number of neighbors. Now, if I take a look at the outer symbols, only the outer symbols, there are 4 outer symbols. How many nearest neighbors do the outer symbols have? How many symbols have a distance d min for this symbol? 2. So, and this is the number of nearest neighbors. outer 4 or symbols. It's concrete. Since 4 of 8 are outer symbols, we say statistically this happens in 4 base cases. So this is the number of neighbors. This is just that this happens in 4 of 8 cases because we have 4 outer symbols in this example. Then we say plus, and then we know and the inner symbols have the same probability that one symbol is wrongly detected as in symbols. Subsection. Then we say inner symbols have 1, 2, 3 Nibs neighbors. Right here, 3 times, and this is again the number of neighbors, yeah? But I have to say for the inner symbols, let's say these are 3 neighbors, 3. Then I weight this. I have the expression. So I could say in this example, symbol error rate, if I put everything together, yeah, this is the same, this is the same. Yeah. Then we get here basically if it's 12 by 16, it's 2, 8 times 16 times this is the same as say, okay, I just calculate this minimum Euclidean distance here as a function of the signal energies. This is quite simple. I just show you the would you do this? I don't do it here. Inner symbols have an energy which is d min by 2. This is one component of the vectors to the square plus d min by 2 to the square. So then you know the energy of the inner symbols. The outer symbols have an energy which is this coordinate here is d min by 2 to the square. Then this is 3 by 2 square. And if I add them, and every cheaper symbol. And then you can try it on your own. If you know that this minimum distance is nothing else, it's square root of 2 times square root of energy per symbol is 3 times the energy per bit because we transmit 3 bits with each symbol. The relation between the energy per symbol and d. Then you also have the relation between the energy per bit. Then you say, hey, now I have the symbol error rate as I wanted to have, because in this concrete case, of square root of, and now I insert this here for d min, square root of 2 divided by 2, square root of 2. That's how it looks. So and you could say, hey, it's astonishing. This 8-level scheme, which reduces the required bandwidth compared to antipodal transmission by a factor of 3, because I increased the symbol interval by 3. This scheme requires nearly the same EB by N naught as on-off keying. This on-off keying, this is on-off keying. It's a bit error rate, which depends this 1/2 here. It's not so important because the error function has a waterfall character. Important is this, EB by 2 N naught. Okay. See exactly the same dependency, EB by 2 N. So the symbol error rate is at least nearly the same as the bit error rate of honor. Let's say nearly this. Now look, now we have the symbol error rate, assuming gray coding, but done. So if assume gray coding, this is what I have done above, yeah. Neighboring symbols only differ. Look, go back in this figure. Neighboring symbols can only differ in one bit. If I take a look at the lower symbols, they only differ in one bit. The red bit is always the same. And here I assign 0, 1, and 1, 1. If I would assign 0, 1, and here 1, 0, both symbols would differ in 2 bits. But I've realized this more clever. So this means if I send this, and if I receive this, I have only 1-bit error and not 2-bit error. Therefore, we use this gray coding. In this direction, it's clear. They only differ in the red bit. This means always, if I get a wrong decision in the nearest neighbor, then only 1 bit is wrong. So this means then, assuming this gray coding, what we are doing, to do this for phase shift keying, these are the most important bandpass modulation schemes. And then we say PB is just 3. See, hey, if I do this, I get here even 5 by 12, which is even lower than 1/2. The error function of 2 even slightly better than on-off keying. Also, I only need 3 times less bandwidth for the same, say, rectangular pulse shaping. If you want, yeah, you can having this approach, yeah, compare the schemes, comparison of schemes. Let's say you could say I introduce an energy efficiency. Yeah, this is just the say energy efficiency of a modulation scheme. Fine, we may define this energy efficiency as the required energy per bit reference scheme. This reference scheme, you may know, which scheme do I choose as a reference scheme? What do you expect? Which is our reference? And we compare all the others with the reference. Just antipodal transmission, not an antipodal. So binary phase shift keying, basically. It's the same. It has the same signal space. So we choose here, this is antipodal transmission. We started with antipodal transmission. And then we compare the required energy per bit of this reference to the required energy per bit of actual scheme, considering. Now look, if the actual scheme requires less energy per bit than then this energy efficiency is positive. It's larger than 1. Requires more energy per bit, energy efficiency is less than 1. Of course, we need to do this, or otherwise this is not fair for N naught. And so we compared for the same bit error rate and for the same noise power spectrum. See, the bit error depends on the noise power spectrum density. And you see, and for this, you always have to consider these factors here. So in order to be precise, let's say, investigations, you have to use the inverse complementary error function and to calculate this EB by a not for bit separate. But you can see, get a very easy estimate if you this factor, the error function, and you only take a look here in this error function, then you say, if I compare, because you know what's within this error function, is this d min by 2. So for the same d min, I get the same bit error rate. Then I say, I basically compare the square of the actual scheme to the, or let's say to the reference distance of our reference scheme. This is antipodal. So this is Euclidean distance. There's only one distance of our reference antipodal mode. This dref is, of course, how large is it? 2 times square root of. This comparison for, so we basically say, for a given energy per bit, how do the Euclidean distances differ? It's the same result. See if it in and E always depend, here is a d to the square depends on EB. So simplify this approach and say, I only compare the Euclidean distances, yeah, for the same energy per bit. So an estimate of the energy efficiency. So, and you see in this case, let's make this example. In this case, this is d min, square root of 2 times EB. Reference, I write it again. Reference, this is equal to square root of. Calculate this energy efficiency, just the approximate is 8 pum. What do I need to do? Insert this d min, the actual scheme. This d min to the square is 2 times EB. Then I insert the distance, yeah. This is 4 times square, right? What do I get? This means this scheme, 8 bar m, requires nearly 2 times more energy per bit than 3 already. This is a quite, now, if you want, yeah, you can investigate. Now, small starts. In the seminar, we discussed. So this is not a touch screen. Seminar, we discussed shift keying. This was quite a good task. Yeah. 7, basically, you can take a look at different schemes. And what is shown is always the signal space in the equivalence range. Bandpass modulation schemes. We do this transform in the equivalence range for this example. Now, this lecture, okay? Now you can switch through the schemes. Yeah. Just offset quadrature phase shift key. So if you want, then you go to a slide which is this. This is what I'm talking about. So I say, okay, our reference is, so I have to share it. So reference scheme is antipodal transmission, or in the bandpass range, this has the same signal space as binary phase shift keying. Then you see basically these estimated energy efficiencies. Population order M for different modulation schemes. So let's say phase shift keying, quadrature amplitude. Oh, what happens if we insert M equal to 8? Do it. So don't do it here. Calculate which scales inversely proportional to M for amplitude shift keying, for phase shift keying, quadrature amplitude. Why you use this high order modulations? You want to decrease the required bandwidth. Phase shift keying, as I said, my opinion, don't know any example where a modulation order larger than 2 is of any interest, because frequency shift keying requires more bandwidth. Bandwidth efficiency today is the most important to achieve for a given bandwidth efficiency, best energy efficiency. If you combine the upper schemes with channel code, they are much more energy efficient than shift keying. So just ignore. Then this is just a table, but if you then you see the results. Here you see the energy efficiency in the reference, yeah, binary transmission. So the order is 2, of course. And the efficiency of, let's say, a 2 QAM is just 0 dB. So it's 1 in scale, 0 dB. Then if I get basically energy efficiency because I increase the modulation order, I need more energy. This is what we know. Yeah? Let's say if I switch from 2 levels to a 64 level QAM, what does it mean? If I use 64 levels, is there a benefit in a factor of 6? Because 64 combinations, 64 symbols. What does it mean? Log 2 of 64 is 6. So I transmit 6 bits with each symbol, so 6 times better bandwidth efficiency than reference. 6 times less bandwidth. So for a given channel, I could transmit 6 times higher bit rate. But I know there is a price, and the price is I need more energy to be put it in 1 bit. So this is about 8 dB quadrature amplitude. See how good this quadrature amplitude. If you do the same for shift keying, these are the values for phase shift keying. If you do a 64 level phase shift keying, you need 18 dB per bit. 18 dB is, say 20 dB is a factor of 100. So let's say this is a factor of, it's not exactly 160 or so, but you need a huge amount of more. But this is energy per bit. Let's say transmit really at a bit rate which is, let's say, 6 times higher. Then we know if you increase the bit rate, given scheme, 6, you usually need 6 times more power, because here you see required energy per bit. Don't forget that. I also change the bit rate from one scheme to another. Here we compare all required energy for 1 bit. But if I transmit faster, okay, then the power to transmit these shorter bits is even. And here you see there's a nice, basically, summary. It's important schemes. Phase shift key, a frequency shift key requires more bandwidth. It's less bandwidth efficient, but it achieves a certain gain with respect to the energy. It's better, it has a better energy efficiency. But I said ignore this. This has no importance now. So and now we go back and just want to discuss a point, and this is how can we power spectral density, for instance, of QAM. To do this, I go back. Yeah, let's say equivalent low pass range. Oh, now we finished basically this energy comparison, neighbor approximation, basis functions. Then low pass. this is quite simple. Always, if you have a bandpass signal, which is basically a modulated version, let's say, of a cosine. Yeah? It's this quadrature up conversion equation, yeah? And you say, hey, then it's quite simple. Obtain the signal, yeah? You get this FC, this example, this is just an example. T, right? 2 periods, simple and all. So, of course, this transform with respect to this center frequency FC. So, and then I have T, this is T, and this would be the first basis function here. This would be C1 low pass of T. So it's real valued and square root of, because our transform needs to ensure the same energy. Yeah? This is done. So now we take a look at the second basis function in the range. And this is just a modulated sine, modulated sine, as you remember. So, and what's this equation? Do you remember that in the bandpass range, yeah, signal is square root of 2 times the low pass signal real times cosine minus square root of 2 times the low pass signal's imaginary sine. So now we have this minus sign. So this gives basically pure imaginary basis function. So I could write this f at j. So and this would be, say it has the same length. T. This would be C2L. This is the second basis function in the equivalent low pass. But you see, this second basis function in the low pass range is just J times C T. So, and we could say, instead of using these basis functions, yeah, two basis function, I could say there's only one basis function, but I have complex data. Because the difference between this is only the J. Then I could say, I put the J just in our symbols to be transmitted, or symbol vectors, as you know from this phase shift keying. Then I don't use this, I just say I don't use an index, it's two-dimensional case, I just say in the range on the sides, this is psi of t. It's just the pulse shape. It could be, for instance, a root-raised cosine pulse. This is just J times psi of t. I don't use this psi1L. This is just our pulse shaping. It's cosine. Here's a rectangle. Then we could say, the QAM signal could look. Now the whole signal, not on short transmission. Let's say this could be UTX of t is equal to sum. Let's say this is the x symbol. K goes from infinity to infinity. Then we say we symbol set k, each weight basis functions, and if these are normalized, these are just numbers, real numbers, normalized, then I need to introduce here a certain energy, yeah, out of an energy to say signal is correct. C of t minus t. This is, of course, in the low pass range here. So this is our signal, yeah, the transmitted signal in the low pass range. The question is, yeah, this E0 is just a certain energy. This energy is just related to the mean energy per symbol. And now we say these set K, how do they look like for level QAM? How do they look like? I just say normalized symbol levels could be, if you say I don't want to write this with bits, I say, for instance, this is normalized -3. This is -1. 1 and 3. Okay. This is minus 1 and just to say normalized levels. Then this, yeah, minus 1 and plus 1 becomes minus j and plus j. Say the symbols are, let's say, I start with this down branch, yeah, where this bit is 0, okay? Red bit, this red. Say this looks like, just do it 3, space here, minus 1, space, 1, 3, space, 3, space, 1, 1, space, 3. Then I put this other bit, yeah, it's a complex number. So let's say minus j, 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 and this plus j, plus j. This doesn't work. This is 3. Switched from real valued symbols to complex values. And if you ask MATLAB or Octave, for instance, and if you start the program QEM mod, then the output is just this mapping real values, let's say 8 values to these complex values. It's just a real to complex mapping. So, and these are the symbols. And now we could say, what is the autocorrelation function of these complex symbols? Then we could say phi set set. Symbols are complex. 5 minutes probably. And so this is the autocorrelation function of the symbols. And remember how to calculate this. This is the expected times zk plus m. So this is the time shift in the index. But take care for complex symbols to use this. So this is, remember, I just tell you this general expression, yeah. This is nothing else than this value is just that square. So this is the expected value. This does it mean that k, so it does not depend on x magnitude square. It's just the second moment. And now let's calculate the second moment. This is quite simple. In our, it's symbols are either minus 1 or plus 1 minus j plus j, these inner symbols. So the inner symbols, let's say, at 1 to the square plus 1 to the square. So this gives 2. So and this is in 1. Outer symbols have 3 plus 1 squares. If you calculate, so what is the magnitude of to the square? Magnitude of, say, here's 3. This is just j. Yeah, this magnitude is 3 plus 1 square root. Plus 1 is 10 times 1 by 4. This gives divided by 4. Sorry, 1 by 2. In half of the case, in half. This gives 12 by 2 is 6. This is the value of the autocorrelation function at m equals 0. Then we need to take a look at m. Then this value is just basically expected set k. Now, remember, if neighboring symbols are statistically independent, yeah, and basically right here at the correlation function, the joint PDF at the products of the PDF. This expected value would be expected value of zk complex conjugated, yeah, and then the other, the expected value of zk plus m, which is independent m. So basically, just to show you this, we get this times, but this is just an intermediate step, and the result is very simple. This is just expected of zk, so we take the average square value of this, but the magnitude. We have to take a look at the mean value. And what is the mean value over all symbols? Our symbols, what is it? Simple, yeah? 0. Yeah. 0 is equal. So this is our autocorrelation function. This is the autocorrelation of our 6, and all the other values are 0. This is the. Now, in order to switch from what we want to know, this is 1, 2, this 1, and so on. What we want to know is how can we find the power spectral density of this? Do this via the autocorrelation function. And the approach is just, again, as you remember, say Tx, okay, here it's in the equivalent. You can write this as separate the pulse shape, psi of t, this is now only psi of t, it's one pulse shape. It only works for such such modulation schemes which are, let's say, linear. Then we do the convolution with square. It's just a certain energy, some k from minus infinite z modulation interval. Then we say, in order to find the autocorrelation function, just write here phi LL of tau. Yeah? Strictly, I don't use this generally. Yeah? To do sign to say, okay, the process is to say cyclostationary. If you skip this line here, ignore it, doesn't matter. Then the autocorrelation function is just phi c psi of tau, so the autocorrelation of the pulse shape. So the pulse shape determines the autocorrelation. The other thing is the autocorrelation function of this sample signal. Let's say this is x delta of, then in the autocorrelation function. Question is, how does it look like? So, and if we switch from this sequence of numbers just to direct delta pulse, this zk, the autocorrelation function, is known. And now we switch from a sequence of numbers to a sequence of weighted pulses. We say that the autocorrelation function now of this x delta looks like this. Always where we have such a component, now just a direct delta pulse, right? Here we don't have a direct delta pulse, don't. And the spacing between these numbers which are generated, spacing is t minus t and so on. And then to write here this 6 as a new weight, this would be x. Now take care, one further step. Always remember, if we talked about periodic signal, switch from the sequence of numbers to a sequence of direct delta pulses. Have to write here the reciprocal value of this separation between the direct delta pulses here in the auto. Since I introduced here this additional, this just depends on how to write this. If you want to say, I want to have this in this expression, let's say we do it like this. Simply say, this is just delta, and of course then we have to write everything. The autocorrelation function depends always on the squares. So it's just, I just say x delta E naught doesn't belong. Then we finished here. So just go from here to here, switch from this, find the autocorrelation function only for time index 1, 2, 3, 4. Here we define the autocorrelation, all values in between. Here it's not, if you take a look here as an expression, it's not defined in between. It's only defined for m equal to 0, 1, 2, 3. Find for all these values. it's like this. It's here 0. Not only t, 2t, and so on. Then, if I mix everything, does it look like the autocorrelation function? In this case of our pulse, it looks like this. Unit energy, it's quite simple. It's this one, yeah? This is minus t for this rectangular pulse shaping. This is tau. Then we need to do the convolution with this, right? To weight with E naught. Therefore, our autocorrelation function, we have the autocorrelation, we also have spectral density. So much. Like, then I do the convolution of this. Also a function which looks like this. This is 1 times 6 by t. Therefore, by the way, we know this is the same as the energy per symbol by t. So now we have the relation between this E naught and Es, because we know the autocorrelation function at tau equal to 0. It's always the mean power. What is the mean power? It's the energy per symbol divided by the symbol interval. Okay, so now we know this E naught is related to Es by a factor of. This is phi. So you have to find the autocorrelation function of the pulse, you have to find the autocorrelation function of the numbers to be transformed. Then you have the our spectral density is just a transform of that. So we just need to spectral density. In this case, it's a sinc squared. This concrete example. CF, this is more or less C required bandwidth, let's say measured here at the 0 crossings, is inversely proportional to capital T. 1 by capital T is just the bit rate divided by S bandwidth is this M. So this is how the power spectral density would be. This number would be in energy, watt per hertz, same as or the power spectral density. Watt seconds is the same as watt per hertz. If I do the Fourier transform of this would be the, as I said, the approach is always the same. Determine the autocorrelation pulse shape, determine the autocorrelation function of the numbers to be transmitted, and both just have to assign directly. So, okay, that's all. And I say goodbye. It was a pleasure to view as audience. During the lecture, all there are only come good through the winter. It's hard in German. Sun probably also. Sure. Okay. Can you, if you really have this question, can you come in my office? Because I have a lecture starting in an hour here at the lecture hall. So I want to go for lunch. I